All right, I think we can go ahead and get started. So welcome everyone to our IAS Astrophysics seminar once again. Today we are very happy to have Katelyn Breivik, who is what is your title? Sorry, Flatiron Research Fellow at the CCA in New York. So Katie finished her PhD at Northwestern a few years ago, and then spent a few years as a postdoc at CETA. And I think very recently, maybe even in the last few months, has moved to our neck of the woods, to the Flatiron Institute in New York. So we're very happy to have Katie today speaking about binary evolution, a multi-messenger, multi-band puzzle. And please take it away.
Thanks, Susan. Yeah, so I just moved here in August, so it's been fun to try doing that in a pandemic. I'm sure other people have done so recently. So today I'm going to be talking about binary evolution, and in particular, I'll be talking both about gravitational waves and electromagnetic observation. So that's where you get multi-messenger, and I will not be thinking about LIGO stuff so much. I'll be talking about LISA, but of course, many of the types of binaries that you would get would become multi-band sources, so LISA sources and LIGO sources. And of course, in order to solve binary evolution, I think we're going to have to use all of these things together to figure it out. Okay, so to start off, to try to convince everybody that this talk is going to be interesting, I will start with a very dramatic statement, which is binary stars are a critical component or limiting factor in basically every area of astrophysics. And if you have an area of astrophysics where you don't think binary stars are important, I would love to talk to you more about it, because I think we can probably find a reason why they are important. I feel strongly enough about this that I got together with Adrian Price-Whelan and David Hogg a few months ago, I guess a year ago, to write a white paper, a decadal white paper that says we should be funding binary star physics instead of the decadal sub processes. So we got a postdoc from every one of the decadal areas to write why they thought binary stars were the most important part of their science, to make our point. We sort of cheated, and we had Cliff Johnson. He actually worked for both resolved stellar populations and galaxy evolution. But in both cases, if you're interested in galaxy evolution, binary stars are doing a lot of work in terms of the stellar feedback that drive that evolution. So if you're not really sure how binary stars work, you're limited by understanding the feedback processes in your galaxy evolution. Of course, most stars have companions. And so if you're interested in stellar evolution, like Jamie Teilhard is, then you care about binary stars. Moreover, one of the best ways to study stars in general is to study them dynamically in binary systems. The thing that I took over was formation of compact objects. Of course, most compact objects that we think about, at least stellar mass compact objects, come from high mass stars, which are all in binaries. If you're interested in star formation or planet formation, these are intimately linked to binary star formation. In particular, Max Moe is finding with his collaborators that if you are forming stars and they form binaries, you're probably less likely to form planets inside your solar system of that star. So that's very closely linked to planetary and stellar formation. Tim Morton has done some work on how understanding characteristics of binary populations is going to become the limiting factor in understanding planetary populations, because binary stars are actually one of the biggest problems with their data analysis so far is false positives. Adrian Price-Whelan and Anna Bonazza, along with many others, are looking for dark matter clumps out in the outer galaxy, and one of their biggest sources of uncertainty at this time is whether or not binary stars are messing up their dynamical observations of stars and stellar streams. And Dan D'Orazio took over the multi-messenger astrophysics, and of course, the binary neutron star is this flagship source of multi-messenger astrophysics, and of course it came from a binary. So literally anything that you can think of, at least as far as we define it in the decadal process, is tied to binaries. So if you're not just excited about binaries the same way that I am, I hope that you will at least agree with me that they're important to understand. A little bit of what I do personally, the things that drive my research is sort of divided into three characteristics. The first is binary population synthesis. So this is what I spend probably most of my day-to-day time doing. I'm working with a team of folks to develop open and accessible binary population software that has easily shareable and reproducible results. This has not always been the case in binary population synthesis work and has sort of been a bit of a reason why folks are a little bit uncertain about whether or not they should trust any results that come from binary population synthesis. So we're working to change that. I spent most of my PhD thinking about gravitational wave sources, and in particular using gravitational wave populations as a tool to do astronomy. That means that I'm not so much a person who thinks about how to detect gravitational waves or what their parameter estimation techniques are or anything like that. It's more, I use the work of my colleagues to give me a giant catalog of compact remnants and binaries, and then try to understand what I can understand about binary evolution or the galaxy or things like that from those observations. And a direction that I'm starting to move in with a couple of collaborators is thinking about what can we do with gigantic binary populations at intermediate evolutionary phases that are observed with astrometry. So I'll touch on each of these throughout the talk. And yeah, let's get started. So first things first, I'd like to introduce the code that I develop on with a bunch of my collaborators. It's called COSMIC. It's a real acronym. It stands for Compact Object Synthesis and Monte Carlo Investigation Code. It's really hard to Google. We didn't know this when we set the name like 5 years ago, so apologies for that. If you want to search for it, search Cosmic PopSynth, that will bring it up. If you search Cosmic, you're gonna find 1,000 other things. Some details that may or may not be interesting to you if you're interested in this kind of stuff are, first, we're based on a widely used binary stellar evolution fit code called BSE. We are fully integrated with CMC, which is Northwestern's globular cluster dynamics code. That means that we can produce apples to apples comparisons of isolated binary evolution and binaries in globular clusters. Most studies are sort of combining different stellar evolution codes with different dynamics codes, and so you're not really getting a close one-to-one comparison. Another thing that we do is we can quantify the convergence of our binary parameter distributions on the fly. And what that means in practice is we try to answer the question, have you simulated enough binaries in your population to adequately understand the underlying physics? Most population synthesis codes just say run 1 million binaries and see what happens. And for the types of systems that I'm interested in, these are the low probability tails, usually, of the binary parameter distributions. So we really want to make sure that we've quantified those well. And finally, the thing that I think that really makes COSMIC stand apart is that we are fully open source developed in Python, and we have documentation and examples, and you can pip install it. So if you're interested in using it, it should be very easy to get started with. This is our team of folks. These are the people who were on the first COSMIC paper that we finally got out this year. Each of these people has contributed in several different ways, but I just wanted to acknowledge all of the work that they've done. Because it's been a lot, and we spent a lot of time working to get that code paper out. If you're somebody who has released software before, you know that releasing software is probably not the same as writing a code paper. And that's why the code paper was out this year and not a few years into my PhD, like I told everybody it would be. Just to give you a bit of a sense of what we've used COSMIC to do so far, COSMIC has been used by myself and Kyle Kramer to study accreting white dwarf populations that will be observable by LISA and Gaia. We've used it to study double white dwarfs that are in detached configurations. We've used it to study accreting neutron star binaries. It's been used by folks at UCLA to study binaries in the galactic center, specifically Smundar Nawaz's group. I've been, as I said, using it with a few collaborators to study astrometric compact binaries, and it's been used in a few LIGO studies so far. So the most recent one I would say is from Mike Zevin, where he studied the formation of the really asymmetric 2.6 solar mass compact object with a 26 solar mass black hole. I'm hoping that it will continue to get picked up so that I can't fit the studies on one slide. So please share widely that it is open and available if you'd like to use binary population synthesis. Okay, so now that we have talked a little bit about what the code is, Everything that I share for the next little while is going to be results that are using populations that are simulated with Cosmic to do some sort of astrophysics. So this first study that I'm going to talk about is my most recent paper that was put out with Chiara Mingarelli and Shane Larson. And this is focusing on looking at galactic structure using just the LISA double white dwarf foreground. So in terms of thinking about galactic structure, most people think of Gaia immediately. I don't blame you. Gaia is the big dog in the game. It knows where most bright stars are in the galaxy. It's got positions and velocities for 1 billion stars, which is just completely unparalleled. We will never do better than Gaia with gravitational waves. However, if you're somebody who's interested in looking at white dwarfs with Gaia, you're going to have a bad time. And that's because Gaia's limiting magnitude is dim enough that you can only get a complete sample of white dwarfs out to 20 parsecs or so. So the white dwarf population that Gaia can observe is down in that little tiny black circle, which means Gaia will not determine the spatial structure of any sort of white dwarfs in the galaxy. It can do really well with very close by, but it won't get galactic measurements at all. Conversely, LISA is a space-based gravitational wave detector that will be launched in 2034. And LISA is sensitive to gravitational waves in the millihertz regime. And the most prolific source of those types of gravitational waves are double white dwarfs in the Milky Way. So double white dwarfs are enormously loud gravitational wave signals in our galaxy. In particular, this is the horizon that you could see a single resolved double white dwarf with a gravitational wave frequency of 2 millihertz. So if you're interested in finding double white dwarfs in the galaxy, you're not going to use Gaia, you're going to use gravitational waves.
I have a question from Roman.
Yeah.
Katie, hi. You started jumping right into the science, but I was actually wondering about the inner workings of the code that you sort of.
Oh, absolutely.
I mean, are you going to talk about this at some point? Like what sort of physics goes in, what happens, you know, how the wheels are turning and so on and so forth?
If I'm honest, most people don't care. So I usually don't talk about it. So
on it till this discussion in the afternoon.
Yeah. So maybe we can leave it till the end. Or if there's something in any case, I'm happy to talk about it a ton. I just usually leave it out because most people get quite bored hearing about binary evolution like codes. Okay. Let's see, I'm gonna turn up my volume just a touch. Okay, all right, so this is our picture. We're gonna use LISA to observe double white dwarfs to try to understand galactic structure. There have been previous studies to study what the resolved double white dwarf population will look like within LISA. There's tons of studies like this. I put out a couple myself. It's kind of like everybody's favorite paper to write when they create a binary population synthesis code. But one study that's really important that's been done is by Valeria Corral, where she counted up how many sources will have position, chirp mass, distance, and sky position measurements that are within 30% by LISA. She also counted up that there will be something like 100 LSST counterparts or Gaia counterparts. It's usually LSST, honestly, because LSST can see farther away. And you will, she also found that if you do concentrated follow-up, we can actually see double white dwarfs a little bit farther away. You just need to have the right telescope to look for them. So if you're looking with large scale surveys like LSST and Gaia, you might not pick everything up. But if you have a resolved source that you know is within the distance that your telescope can see out to, then it's a lot easier to find them. So in terms of what we will understand about double white dwarfs, before 2034, it's not going to change so much, but after 2034, we're literally going to have an enormous catalog of close double white dwarfs in our galaxy. So what I'm showing in this figure is just the XY projection of our galaxy. So we're sort of looking straight down onto it. And this is from Valeria's simulated population from a code that's called SIBA. And these are the number of double white dwarfs that are resolved. So you can see in the color, this is gravitational wave sources, and in turquoise, this is our EM counterparts. And so one thing that really highlights here similar to what I showed before, is that LISA can see double white dwarfs basically anywhere in the galaxy, as long as the frequency is short enough. So if you're really within LISA's frequency regime that it can see things quite well, you're going to see double white dwarfs all the way across the galaxy. And in particular, you're not going to be obscured by things that most stars are obscured by. So specifically dust, we don't have to worry about whatsoever. It doesn't matter. You can see any double white dwarfs in the bulge, through the bulge, on the other side of the bulge. So Valeria took her galaxy and she used some simplified galactic spatial distributions to see how well LISA can reconstruct those spatial distributions just with these resolved sources. And what she found is that you can do these reconstructions to an accuracy of about 10 to 100 parsecs. This is not great when you're considering what Gaia's resolution is. So Gaia is going to be measuring star positions and these types of galactic spatial distributions to 1 to 5 parsec accuracy, because it can literally see the positions of each star. But for double white dwarfs, that's pretty great because you're doing the same measurement and you can consistently see whether or not the resolved double white dwarfs track these bright stars. So we wanted to expand on this using the double white dwarf foreground, and I'll explain now what that actually means. So what this is a standard amplitude spectral density curve of the galaxy of double white dwarfs. So this is something that's really common to see in LISA talks and not common to see basically anywhere else. So I'm going to go really carefully in detail here. So on the x-axis, this is our gravitational wave frequency. And on the y-axis, this is our amplitude spectral density. This is a measure of strain, gravitational wave strain. But in LISA, what this measure does is it also brings into account how much time a binary sits at a given frequency and radiates gravitational waves. So what it's doing is effectively accounts for how much time you're observing and gives you a closer understanding of what the signal to noise is. So much so that if you look at the blue lines, that's the galaxy signal in double white dwarfs, and the black line is the LISA sensitivity curve, and how high the blue line stands above the sensitivity curve is basically its signal to noise ratio. So when I say double white dwarfs are loud signals in LISA, what I mean is that they're literally signal to noise ratios of 1,000 or better, depending on your frequency. So fantastically loud signals. Some quick characteristics. Number one, double white dwarfs start to interact around 10 millihertz, this gray line. That's why there's this just like very sharp cutoff that you see. That's because for this study, I pulled out any interacting double white dwarfs because we weren't treating them carefully at the time. And so we didn't want to give false understanding of what's going on there. Oh no, I'm going backwards. What? Okay. Below something like a millihertz, this is where double white dwarfs start to become unresolved. And what that means, the difference between unresolved and resolved, is that LISA can observe a gravitational wave signal at a given frequency and tell that there is a single double white dwarf that is creating that signal. So above 1 millihertz, double white dwarfs start to become resolved, both because their signal is higher, because the sensitivity curve drops, so you're getting a better SNR, but also LISA's frequency resolution is such that you have more opportunities to measure a double white dwarf in a given LISA frequency bin. So LISA's frequency resolution is 1 over its observation time, which means that the frequency width that it can resolve gravitational wave signals from is roughly around 10 to the minus 9 hertz. So it's like a really fantastic frequency resolution, but the punchline is basically that between 10 to the minus 4 hertz and 10 to the minus 3 hertz, you have 10 times fewer frequency bins to be throwing double white dwarfs into for LISA to resolve. This is compounded by the fact that the way that gravitational wave emission works means that you have fewer and fewer double white dwarfs spending time at higher frequencies. So you get an enormous pileup of double white dwarfs at frequencies below a millihertz. The farther out you go, the more double white dwarfs there are, and that's what causes I wonder if you can see my cursor. That's what causes this specific peak or this specific line here. This is a astrophysical noise floor that's caused by the double white dwarfs. If we fly a better LISA and its sensitivity curve comes down here, there is an astrophysical noise floor that you will have to subtract out no matter what happens because there are so many double white dwarfs. Okay, so Valeria covered the resolved systems above 10 to the minus 3. Really, it's closer to a few times 10 to the minus 3 hertz. But Chiara, Shane, and myself wanted to look at what you could do with this signal that's unresolved down here, because most people tend to just think of it as like trash in the LISA data that they want to get rid of. So the first thing that we realized is maybe you could measure galactic structure. And the reason for that is because if you change, oh, excuse me, I was supposed to show you this and I just talked through it. There are literally, one of the other reasons that we care about the unresolved foreground is that it is the bulk majority of the double white dwarfs in the galaxy. There are only a few, tens of thousands of double white dwarfs above a millihertz, and literally millions of double white dwarfs in the unresolved foreground. So if you want to learn about bulk statistics on the double white dwarfs, you have to go unresolved. Okay, so back to my story. So we realized that if you change the distribution of double white dwarfs from our simulated populations, you can see it very obviously. This isn't like a shocking result by any stretch, but the distribution of gravitational wave power on the sky really strongly depends on how you distribute double white dwarfs on the sky. And so we decided to see if LISA could do similar types of galactic spatial constraints as what Valeria had done, but just with an unresolved gravitational wave signal. So what I'm showing here is this amplitude spectral density again for everything below a millihertz. So this is a little bit inflated because you would observe in a given frequency range, but it's used to show the point, which is that if you assume double white dwarfs follow bright stars, or you assume that the bulk double white dwarf population is vertically heated from whatever type of your favorite dynamical interaction could be over time, then we wanted to know, we know that this looks different here, but we wanted to know, can LISA tell the difference between these?
I think Roman has a question.
Yeah.
Yeah, I don't quite understand what's plotted here. What are the coordinates and
Oh, yeah, this is just galactic coordinates.
And what, from which vantage point are we looking in what direction?
This is, good question. This is the x-axis versus the z-axis. So we're standing edge on to the galaxy.
And looking at its center?
Yeah, straight pancake on.
Okay.
So this is the galactic plane.
And if you look away from the galactic plane, we wouldn't see much of a signal then? So all of the signal is in the center?
The majority of the signal, yes, is in the center, just from like standard galactic profiles that go like 1/r and 1/z.
Okay. And this is unresolved sources?
That's right. Yeah. So this is not picked up. This is just gravitational wave power on the sky.
Okay.
Thanks. Yeah, totally. Okay. So we wanted to ask, what can LISA constrain? So this is the other thing that I've skipped over that if folks are interested in, we can talk about it at the end, but we took into account what LISA's spatial sensitivity is across the sky using the formalism that Chiara Mingarelli came up with to decompose the sky in gravitational waves down into spherical harmonics. And so this is very similar to what folks in the CMB community have done with the power spectrum, but it's very much less resolution. So what LISA is sensitive to is only L equals less than 4, and that's because LISA is a single detector that's just looking at the sky. It's not, you don't have good correlations to go across. So if you take these two models where we assume double white dwarfs follow the bright stars or they are vertically heated away from the disk, you can decompose this power onto spherical harmonics and then reconstruct what LISA would see in the multipole moments of those spherical harmonics. And it turns out the only ones that really mattered for us are the L equals 4 multipole moments. So when you're asking what LISA can constrain, I have my 4 multipole moments, and really the only ones that show this finest structure are n equals 3, n equals plus and minus 3, and n equals plus and minus 4. So what I'm showing here is what Lisa would measure with my x's for each multipole moment, knowing how much power is on the sky. So you can reconstruct that. You can just say, given the height of Lisa's amplitude, I'm going to project this into spherical harmonics and say this is what my multipole moments are. And now if you vertically heat the galaxy away in varying levels of scale height, z sub h, you're going to get, my brain is failing me. So if you vertically heat away, there's going to be some measurement that Lisa will observe. And if our prior is that it should be here, if the galaxy of double white dwarfs follows the bright stars, this is what you should see. Now, if we place our simulated models on, this is what Lisa would construct if the double white dwarfs are vertically heated away from the disk with each scale height along the x-axis. The error bars are how well Lisa can make this multipole measurement. So if Lisa is able to constrain, these are 1 sigma measurements as well. So Lisa's resolution is honestly really quite poor when you try to do this. But if you are able to constrain this measurement away from what is expected from the bright star distribution, then that's where we say Lisa can tell if the galactic distribution of double white dwarfs is different. And just to help, I've highlighted which ones are and are not constrained or distinguished by Lisa. So if you want to tell whether or not double white dwarfs are heated away from the disk, they're going to have to be vertically heated away by up to a scale height of something like 600. We assume that the double white dwarf, the bright stars, have a scale height of roughly 300 down here. So our resolution is between 300 and 400 parsecs, which is not ideal compared to what Valeria is doing. So I can show you our comparison here. So when you combine everything together, you can use our double white dwarf foreground technique here. We did the same type of measurement that I just showed you 1,000 times with 1,000 different galaxy realizations, and counted how many of them were resolved away at what scale height disk assumption. And depending on how confident you are and how lucky we will be, it's something like between, you have to have a vertically heated disk between 550 to 700 parsecs, so 250 to 300 parsec resolution. When you compare that to Valeria's measurements, which are something like 50 parsec resolution, it's not great. And then when you compare to our bright stars, it's just really not great at all. However, there is a silver lining here, which is if you go from here to here to here, and you get increasingly better measurements that center in on each other, then you know that the double white dwarfs in the bulk population, in the resolved population, and in the bright stars, everything has the same galactic structure, you'll be able to tell. If instead we get different structure here from the resolved, if you get different structure in the bright stars versus the resolved double white dwarfs, that will tell you something. And if you get different structure between the resolved double white dwarfs and the foreground, that really tells you something, because that tells you that the bulk population is not distributed in the same way that the resolved population is. So even though the resolution isn't incredible, we do think that it's still worthwhile to make this type of measurement. Furthermore, if you're somebody who does want to get rid of the double white dwarf foreground, in particular, if you are a cosmologist who has a cosmological background that Lisa will observe, in many situations, these are distributed, these are studied in terms of spherical harmonics as well. So you might just want to subtract out our the multipole moment measurements instead of the white dwarf resolved measurements. Okay. That, I think, yeah, that's everything that I have for the double white dwarfs. So for the rest of the talk, I'll focus on astrometric binaries. So if you have questions about double white dwarfs, we can talk about them now or wait and go to the end. It just depends on what people think.
Can I ask just a naive background question, which is how how do double white dwarfs compare to other stellar populations for probing things like this disk heating?
Right. So for the bright stars, these are usually going to mostly be young stars, and the double white dwarfs are they're just the older population. So double white dwarfs trace stars over several giga years in the past, and the bright stars trace recent young stellar populations. In terms of massive stars, you could do something similar with black holes and neutron stars. Unfortunately, LISA just doesn't see so many of them that you would be able to make this kind of measurement to begin with. Yeah, so with double white dwarfs, there's something like tens of thousands. With neutron stars, maybe a couple hundred. So you could do a resolved type study, and with black holes, it's like maybe dozens if we're lucky. So yeah, definitely there is no foreground from anything but double white dwarfs.
Right, okay, great. Thanks.
Yeah, totally. Okay. All right, so this is actually mostly the bulk of my talk. As you can see, this is really what I've been thinking about over the past couple of years. Part of the reason for that is that I need to get, if I'm staying in academia, I need to get hired with something that will have data before the next 15 years. So I started thinking about things that are coming out more rapidly, and part of that is Gaia data. So for the rest of the talk, I'll be talking about work that I've been doing with Jeff Andrews, Saurabh Chatterjee, Saurabh's student Chirag Chawla, and then my thesis advisor helped with some of this stuff while I was still at Northwestern, Shane Larson. Okay, so I think, and this is why I'm spending a lot of time doing this, that discovering compact objects orbiting luminous companions that are not in contact will completely transform our understanding of binary interactions. The reason for this is that we don't actually have great observations of most binaries at a bunch of stages in their life. So what I'm showing is like a traditional marching left to right. This is how a high mass binary would go through its life. It would start out at zero age main sequence. You'll probably undergo some type of mass transfer where the more massive star donates mass to its companion. This could lead to a common envelope, which will bring the stars very, very close together. Or it could go through stable mass transfer, which also will bring the stars closer together, but not so bad as a common envelope. This will leave behind something like a strip star plus a luminous companion. Eventually, the strip star will evolve to become a compact object, and then it will have a luminous companion with it. That luminous companion can then undergo mass transfer back onto the compact object, leaving behind a compact object and a strip star. And then eventually that strip star can also become a compact object. This is like a standard, this is how you would make, for example, what I've drawn here is a black hole neutron star binary. The boxes are to indicate which phases have actually been observed well. So we've seen zero age main sequence or young, not interacting massive stars out in our galaxy. I think a lot of observers who do stellar observations would say this is not well observed either, because the number of massive stars that we've observed, the catalogs are on the order of dozens. Hopefully this will get better once Gaia releases data. We've observed something like 3 strip star plus luminous companion binaries. Interestingly, these types of binaries are every single one of them so far has been claimed to be a black hole candidate, but it ends up being followed up and they find that it is a stripped star that is the dark remnant companion. So that's sort of an interesting thing that we're finding, is that this phase of evolution we actually have observed, thinking that it was a compact object plus luminous companion. There are a bunch of X-ray binaries out in the galaxy. This phase is actually really easy to observe and understand, but I've still sort of put it in a not fully shaded box because X-ray binaries are notoriously difficult to actually understand their constituent components. So every X-ray binary, unless it's a low mass X-ray binary that's in a specific type of orbital configuration where you can guarantee what its evolutionary history was, measuring the masses of these objects is really, really difficult. And that's just because the accretion processes are very complicated and translating those accretion processes into X-ray emission and then mapping out a mass of a compact object from that is just radically difficult. And so most black hole candidates end up becoming not black hole candidates, and they are confirmed to be neutron stars just because X-rays are really hard. And then finally, we've observed a few compact object plus compact object binaries with LIGO. This will of course become enormous as the years go on. But one thing that I want to highlight here is that in this box, every single one of these types of binaries can have dynamical mass measurements made through astrometry. So if you're looking to characterize these kinds of binaries, astrometry is an extremely powerful tool because you will get, just by virtue of Newtonian dynamics, like Keplerian orbits, this kind of stuff, you will get mass measurements, which is something that you haven't been able to do before. And not only that, but you get mass measurements at several intermediate phases of evolution, which I think is very powerful and will be very helpful in trying to understand the physics that define how each star goes along each of these processes. So what does this actually look like? Compact objects in orbit around a luminous companion, if you think about what Gaia sees, is just, it's literally going to cause a gravitational pull on a luminous companion. And depending on the orbital configuration and the proper motion of your star, Gaia is going to see completely different signatures, which I just think is fun. And yeah, so this is a plot that we put together with Jeff Andrews, showing the signature of a 1 solar mass compact object, a neutron star orbiting a 1 solar mass companion. And so every row is a different proper motion. So there's 10 milliarcseconds per year on the top row, and then 50 milliarcseconds on the bottom row. As you go from left to right in columns, you're looking at different orbital periods, and the X and Y axis are just the position of the binary if you're looking at it sort of face on. So this is like what Gaia would see. On the left-hand side, if the orbital period is, oh, and actually let me say before I move on, the red arrow in every single one of these is the center of mass motion of the actual binary. So the black points are what Gaia will observe, and the blue thin line is the actual trace of the orbit that a luminous companion would take. So if you're looking at orbits that are shorter than a year, parallax is going to dominate your motion. And so the corkscrews that you see are from parallax, and then they move forward because of proper motion. And then the little tiny oscillations around the corkscrew are binary motion. You can see in the middle two panels that parallax and proper motion start to interplay with orbital motion very strongly. So between 100 and 1,000 days, Gaia's going to have to do a lot of work to actually subtract out the parallax from the orbital motion. But these are the binaries that I think are going to be the best to resolve because they are well resolved within Gaia's lifetime. And hope is not lost because parallax, luckily for us, operates on exactly year-long time scales just because of how the Earth orbits the sun. You can see on the far right, if an orbit is in 10,000 days, really any motion that you're going to see is mostly going to be, it'll look like the parallax motion that you see in the corkscrew. And then we made this plot mostly to show people that they should be concerned about the fact that binary motion can make it look like proper motion. So if you're not careful, Gaia might be constraining proper motion improperly for very wide binaries.
Sukanya has a question.
Yeah.
I think you said this and I just missed, what is the difference between the top and the bottom plots? And
oh yeah, go ahead, sorry.
And the other question I was going to ask you is, from this astrometric diagnostics, is it correct that all of them have been, the ones that have been found this way are black hole candidates? Because you in principle, identify, luminous variables and that kind of stuff, right?
Absolutely, yeah. So the difference between a compact object and a luminous companion, is that the compact object should, in principle, not be showing any emission whatsoever in Gaia. So that's what we're focusing on here. Gaia will observe binaries of all kinds. Yeah, definitely. And the top row is a proper motion of 10 milliarcseconds per year, and the bottom row is 50. Okay. So that's why you see a more exaggerated, like the arrows are longer, for example.
Thank you.
Yeah, totally. Okay, so this is kind of like what Gaia will see when it gives us binaries. Full disclosure, Gaia has not given us binaries yet. These are all still simulations. But part of the work that we've done is to ask how well can Gaia characterize the mass of unseen companions? And that's what this next figure is. So luckily for us, we're working with, again, simple Keplerian objects where you're just trying to understand what the mass M2 is of your companion to whatever bright star you're observing. And so here in our grids, I'm showing the fractional mass measurement. So this is to what percentage can you measure this mass quantity M2 over the total mass? This is a lot like what a radial velocity measurement would give you, just without the Sinai degeneracy, because we're not looking at radial velocities, we're actually watching orbits trace. So in the top row, we have a luminous companion with 1 solar mass, and in the bottom row, we have a luminous companion with 10 solar masses. And then each column is the non-luminous companion, so some type of compact object or dark stellar remnant. So in particular, in the left, we're thinking about brown dwarfs. In the second panel at 0.6, we're thinking about white dwarfs, neutron stars, and then black holes. And the punchline here is that for varying distances, so that's what each line is, you can make mass measurements on this quantity without doing any follow-up with Gaia whatsoever. So you can make a dynamical mass measurement out to kiloparsec scales, for example, in this case, to 10% with a 1 solar mass object orbiting, say, a 10 solar mass black hole. We did this study thinking that Gaia must have already done it, and we asked the Gaia folks and they said, we have not. So you should definitely publish this and just let people know what is possible, because people aren't really thinking about it. So we did that. And then with this in mind, we actually simulated a population of black hole plus luminous companion binaries to see how many of these things you actually might expect from Gaia. So, oh, of course, like I said, black hole luminous companions. That's what I'm excited about because I come from the compact object realm. So we did this back in 2017, actually. We simulated a thin disk Milky Way with constant star formation history at solar metallicity. And then we did a, oh, that should say, great, love that. This should say thick disk, which has 15% solar metallicity with a burst of star formation 11 gigayears in the past. These are just contours of the absolute number of black hole luminous companions that we project to exist in the galaxy today. Some things to note are, first, on the x-axis, this is log orbital period. We do not place our binaries in a galactic potential at all. Very nearly most of these types of binaries here would be tidally ripped apart in a galactic potential due to flybys from other stars, anything like that. You'll see why we didn't really care so much about that in a second. This is the mass of the luminous companion. So unsurprisingly, our burst of low metallicity, thin, thick disk star formation gives us low mass luminous companions. And our constant star formation gives us a little bit more massive luminous companions here. These swaths, these are luminous companions that have transferred mass onto their compact object, so they've lost mass. That's why they have just very, very tiny masses. And the other really interesting feature here is right around a year, this is a defining line between binaries which have not undergone any interactions and binaries that have. So the discovery space is very rich.
We have another question here.
Yeah.
So Katie, I think what I was really wanted to ask you is that, have you done a sort of proof of concept, the method, the astrometric diagnostic, can equally well be applied to luminous companions. So that's what I was wondering about.
Right. We haven't yet because so this has been done for Hipparcos for a very small number of binaries. There were no black holes discovered in Hipparcos, which is interesting, but the Hipparcos reach is tiny.
Sure.
And we haven't done anything with Gaia yet because Gaia has literally not given us any binaries.
I see. Thank you.
Zero. Yeah, we're chomping at the bit to get the Gaia binaries, and it's just they haven't given them to us, and the reasons are not unfounded. It's extremely difficult to do their analysis process in general, let alone adding binary motion to it. But yeah, in the future, that's next couple of year work once we get the binaries.
Thanks.
Yeah. All right, so this is our simulated population. If you look at what's possibly observable with X-ray, or sorry, with LISA, this is the LISA upper frequency band. So down here, these are actually literally just like low mass X-ray binaries. Low mass X-ray binaries are known to kind of be potentially observable by LISA if you catch them at the right phase, but it's missing most of the black hole plus stellar companion population. Similarly with X-rays, again, very short periods, but if you overlay Gaia's potential sensitivity, it picks up all of these post-interaction binaries. So this is really what's been driving us to think about this more and more over the past few years. We did this same simulation with several different compact object Higgs strengths. So here we assumed that black holes form with no natal kicks. Here we assumed that they form with neutron star natal kicks. And here we assumed that if mass falls back onto the black hole, it's going to reduce the velocity of the natal kick by conserving linear momentum.
Roman has a question.
Can you use, I mean, you showed that, Gaia can perform well around sort of 1 year. I mean, there are some sort of detections or claim detections of black holes around the spectros, I mean, around, well, in non-interacting spectroscopic binaries. I mean, there are obviously there's a whole bunch in one of the globular clusters that have been announced recently. This is kind of a whole different subject, I mean, globular clusters, but in the field, there is at least one system, Thomson et al. And so on and so forth. So how does that feed into, what you are showing in particular in this kind of gap around 1 year? I believe what has been so far discovered is actually around 1 year. And so the fact that some systems are found where you are predicting they should not be sitting, I mean, that's sort of interesting. Maybe there are some biases and so on, I don't know.
Yeah, definitely. So this is, in particular, this is just the galactic distribution. This is not filtering this is not overlaying any observational constraints on here. So that we do still get binaries right here. But I don't have time to talk about it today, but I do have a paper on the Todd-Thompson binary. And we studied it, and in particular, what we found is that any binary like the one that Todd found had to have undergone a common envelope, according to our models. So it is a post-interaction binary where the black hole progenitor is what caused the interaction.
So are you saying that this, I mean, wait a second. So you're saying that this binary is not what they found, or?
No, it is. So our simulations can make binaries that look like Todd's binary, and we can fit all the constraints within, some few sigma of his observations. And what we found is that every single one that fits it, but also every single black hole plus giant star that is in that regime, the black hole progenitor had undergone a common envelope with the giant star progenitor to bring them to the orbital period configuration.
I see. And so what you're showing here is sort of the binaries which have not undergone any interaction.
Yeah, so these out here at above 1 year or so didn't undergo interaction, and here they have undergone interaction.
Okay, so his binary should still be in this sense, somewhere in this.
Yeah, his binary lives like right around here.
Okay. Okay, thanks.
Yeah. So this is our discovery space that we're quite excited about. I will place some very strong, serious theorist caveats on this that I have been bashed about the ears about since 2017. Oh, wait, sorry, I should just, before I do that, this is Gaia's constraints again, just to remind you. So Gaia really is looking at these post-interaction binaries. And our caveats, oh my word, I have like completely forgotten the organization of this talk. First punchline, Gaia, regardless of our kick strengths, is going to observe a bunch of these. So these numbers that we have are black holes plus luminous companions with orbital periods less than 5 years. Their luminous companion has a Gaia brightness such that Gaia can observe it. And then the numbers, the relative numbers here, are for different resolutions of orbit size that Gaia can tell. So solid lines are the orbit is the same size as Gaia's single observation resolution, which is honestly pretty optimistic. But the more pessimistic, the dotted lines, this is Gaia can actually resolve the observation quite well. So as a function of increasing magnitude, of course, the number goes up. But the punchline is that the bottom of our number is something like 1,000. So this study effectively convinced us that this is the region of astronomy to be thinking about, because these types of binaries exist in configurations that are observable by Gaia. The first few times I showed this, I showed it to theorists. They were like, cool, let's do it. And then observers were like, you forgot a lot of things. So in particular, our star formation history is very simplified. We didn't include dust. This is the one that gets us every time. Everybody's very upset about us for doing that. And we didn't make assumptions on whether or not the black hole mass can be confirmed to be a black hole mass. Of course, I'm showing you these caveats because we started thinking about them. So for the rest of the talk, I'll just show some preliminary work that Chirag has been running. In particular, we've taken our cosmic models. We have assigned fire star formation histories to them using the Latte suite, specifically M12I. And then we've used dust models that have been put together by Joe Bobie in a Milky Way dust Python module to get metallicity dependent ages, positions, and reddening for our black hole luminous companion populations. So what I'm showing you now is just what this looks like with a more complicated star formation history that is dependent on metallicity. And these are the black hole luminous companions that we can observe from this model. So the binary evolution didn't change much, but we just got better star formation histories, reddening, things like that. And yeah, so one thing to note here is that the scale changes dramatically from what all black hole luminous companions are to those that are observed by Gaia. The Earth, we assume, lives right around here. And of course, as with most models, everything is concentrating right here around the bulge. This is where the reddening is supposedly going to get us. When you take all of these constraints into account, you can then count up in a similar way to what I did before as a function of Gaia G, how many black hole plus luminous companions are observable. We again have our optimistic solid cuts and pessimistic dotted cuts. And then red shows black hole plus main sequence and blue shows black hole plus post main sequence. So if you just do the cuts, and then we extended it to 10 years because Gaia was extended to 10 years of observation. So these are the previous cuts that we had. If you update your star formation history, you decrease 1,000 down to something like 720. If you include reddening, it actually doesn't hurt us as bad as we thought. So reddening cuts us down to between 300 and 500. And then requiring that you measure a black hole minimum mass of greater than 5 to call it a candidate is really what gets us in the cuts. So the punchlines here are that depending on how stringent you want to be with Gaia resolution, we think that there are going to be something more realistically like 250 to 400 black hole binary candidates without any extra follow-up from Gaia. And these are spanning several orders of magnitude in metallicity. So it's a really, really fantastic sample of black hole candidates to come. So with that, I'll just leave up summaries of all of this, my 3 things. For population synthesis, if you have ideas and you'd like to make binaries, consider using Cosmic. Reach out to me if you're not certain of the barrier to get over it. In terms of doing astronomy with gravitational waves, I think Lisa is going to be a complete game changer in terms of specifically finding double white dwarfs and doing astronomy with those double white dwarfs. And a little bit closer to us in the next 5 to 10 years, Gaia is going to become a powerhouse of discovering black holes in binaries. And with that, I am finished, and I'm happy to take everyone's questions.
Thank you. And yeah, we have time for some questions. Go ahead, Sakanya.
So I think this is along the lines of what Roman was asking as well. I'm just curious how this is different from, like Chris Belchinski's work, for example.
Right. Okay. So this is in cosmic. So the main difference between using Star Trek and using cosmic is barrier to entry. Belchinski's code is not public. Star Trek is not public, has never been public, will never be public. And to use it, he has complete control over how you use it and what you can publish with it. And we have completely decentralized that altogether. So the only thing that we ask is that you cite our paper and that your results are also public. Like anything that goes with cosmic has to be public and shared. That's the main difference. The physics difference is honestly not much different, like at all. So we use the same exact stellar evolution under the hood, same stellar evolution tracks. There are minor differences in how we calculate mass transfer, but I would argue that our uncertainties of how we calculate mass transfer are high enough that it umbrellas the differences in our mass transfer calculations. Yeah. So there is another open code that just recently came online called Compass. If you are a person who is comfortable with C++ and would prefer to use C++ instead of Python, which wraps Fortran, you can use Compass too. But the installation is a little bit more along the lines of like a Mesa or like more involved installation. So the main thing that makes us stand apart is actually not so much physics. Everybody uses the same physics. It's accessibility and ease of use.
Thank you.
So effectively, this cosmic is like a mass. I mean, for binary evolution population synthesis is like MESA for single star stellar evolution.
We're trying to do that. Yeah,
are you actually using MESA? In following the outcomes of stellar evolution.
We do not, and that's because our fits are our stellar fits are using Peter Eggleton's stars code. And so if you try to do binary evolution integration with MESA, you have different stars under the hood, which are going to behave differently than the stellar evolution that's in our fits. And so I actually would encourage people to probably never do that with cosmic. You should use the same stellar evolution code to do the same types of interactions. Because if you don't, then you're kind of getting into like everything is uncertain with stars, but combining codes makes it an order of magnitude uncertain just with one step. So one thing that you can do that we have done in the past is you can create a population of, say, double white dwarfs, and they start to interact. This is what Kyle and I did. And then you can take that population and do careful dynamical calculations of mass transfer once you have the double white dwarf population. But any sort of like in between binary phase stuff, I would say is a little bit dangerous.
Any hopes for a code comparison project between different groups, including the non-public ones?
Yeah, that's a question we get a lot. I'm open to it. A lot of people sometimes are not. The other thing to note is that this has actually already been done. So Sylvia Tunin did this in 2014. It's called Popcorn. And she got together, she actually did get somebody who had access to Star Trek to agree to do it. So they compared Star Trek, SIBA, and something called binary C, which is very similar to actually what Cosmic uses. And they found that if they could all agree on the same model, they can reproduce the same results. And so the difference between binary population synthesis codes is usually more about what your favorite model is than what the actual code is doing. Which, yeah, it's fantastic. It's funny because I bring this up all the time at conferences, and the more senior people always say that was the most difficult thing that she's ever done. It's a total waste of your time. Just do science. Like, but I think that, yeah, maybe it's a just like difference of how we do software development now versus in the 70s that has just maybe like changed. And hopefully I can convince other people to do that, because I do think it is worthwhile. But the first step is making it public. So at least we've done that.
Good.
Okay, fantastic. Let's thank our speaker again. And I want to remind everyone that we're having a group discussion with Katie at 3 p.m. on the same Zoom link. So hope to see people there.